Hello! In this video we will learn about inner automorphisms. Our outcomes for this video are to learn the vocabulary associated with conjugation by group elements, inner automorphisms, and the inner automorphism group, to learn how to produce specified inner automorphisms, and to answer questions that require you to recall or apply fundamental facts about inner automorphisms and their group. In the last video we learned that the automorphisms of a group form a group themselves, and we saw some examples like these of automorphism groups. Now, referring to these specific examples, I mentioned in the last video that determining all the automorphisms of an arbitrary group is often a lot of work, both in finding the automorphisms and then in proving that you have a complete list, that you haven't missed any of the automorphisms for the group. We did see in the last video a complete answer to what the automorphism group is for finite cyclic groups. However, most groups are not cyclic, and we haven't talked yet about how you can come up with even one non-trivial automorphism if the group is not a finite cyclic group. So we'd really like to answer this question. Is there an easy way to come up with non-trivial automorphisms? Well, the answer is yes, at least sometimes. And the purpose of this video is to talk about the way in which that can be done. Given a group G and an element little g, the inner automorphism of big G induced by little g is the function phi sub g mapping G to itself, defined by sending each element x of the group to the element gxg inverse. Now there's a bit to make sense of and a bit to comment on in that definition. First, we'll add some more vocabulary to the slide. This operation of mapping x to gxg inverse is called conjugation by little g. It's the main idea behind the inner automorphism, and we will definitely see it again as this class goes on. You may have also seen it before in a linear algebra class, such as when a matrix is diagonalized. It's a very fruitful idea. What can inner automorphisms look like in practice, though? Well, here's an example. We're showing here the inner automorphism of the symmetric group S3 induced by the cycle 2,3. Conjugating the cycle 1,2 by 2,3 produces the cycle 1,3, and conjugating 1,3,2 by 2,3 ends up giving us the permutation 1,2,3. If we write out the results of conjugation by 2,3 on every element of the symmetric group S3, we get the display here, where the elements in the first row are each sent to the element underneath them, and we see that as we saw above, 1,2 is sent to 1,3, and 1,3,2 maps to 1,2,3, but the other elements are also written out. More generally, why does conjugation by little g produce an automorphism of a group big G? Well, I'll leave it to you to prove that the map phi sub little g maps big G into itself and is one-to-one and onto. The cancellation law for groups we saw at the beginning of the semester will be helpful. Let's just take a look right here at why the maps phi sub g will always be operation preserving. If A and B are any elements of big G, then phi sub g of AB by definition equals G AB G inverse. Well, this expression is equal to the next door expression, where we insert G inverse G between the A and B, which allows us to conclude that phi G of AB is equal to phi sub G of A, phi sub G of B. Now, keep in mind that we can do this conjugation by any element little g of the group, and we will always get an automorphism. However, it is possible that conjugating by two different little g's could end up producing the same automorphism. In fact, all elements of the center of G will produce the same inner automorphism. You'll remember that the center of G consists of all the elements that commute with every other element in G. So if little g is any of those elements in the center, then the inner automorphism induced by little g ends up sending x just to itself because that g commutes with the x. In other words, every inner automorphism using an element of the center produces the trivial automorphism. Now, when we looked at all the automorphisms together in the last video, it turned out that the whole set of automorphisms of a group G was itself a group, the automorphism group of G. Let's define in of G to be the collection of all inner automorphisms of G. It turns out that like aught of G, in of G is a group. It's called the inner automorphism group of G, and it actually is a subgroup of aught of G. Now I'm going to leave it to you to come up with a proof that in of G is a subgroup of aught of G. You should probably approach this by using one of our subgroup tests. Go ahead and review those if you're a little bit rusty on how to apply those. Well, it's time for a few more notes. First, if G is abelian, then every inner automorphism, V sub G, is the trivial automorphism. This makes in of G a trivial subgroup of aught of G when G is abelian. Next, as we will see in a little while, there is a nice connection between any group G, its center, and its inner automorphism group. We don't know enough to say what that connection is just yet, but it's coming, and it applies to all groups. And with that, we reach the end of this video. To recap, we've talked about conjugation by G, inner automorphisms, and the inner automorphism group. Please make sure that you've mastered this vocabulary. Please also make sure that you know how to compute the images of inner automorphisms induced by elements of G, and know some basic facts about the inner automorphism group, in of G, such as that it is a group and that it is a subgroup of aught of G. And that will do it for us until next time, when we will introduce the important new idea of cosets. Until then.